Objective 1, perform operations with complex numbers. I'm going to break this objective up into two videos. So by the end of the second video, you should be able to work with this objective. I can add, subtract, multiply, and divide with complex numbers. Now, before we begin actually doing that, we need to talk about what a complex number is. Up until now, we've been solving with factoring, strategies of factoring, and those solutions that we've been working with have all been real numbers. They're x-intercepts, they hit the x-axis. Sometimes, though, we will encounter equations that have no real solutions. So mathematicians, way long ago, had to create a whole new set of numbers to satisfy this situation. So they had to rely on a number system with the imaginary unit indicated by the letter I. Congratulations, you have entered into the realm of imaginary numbers. You can consider yourself now a mathematician, but also a math nerd, because now you're going to be talking about imaginary numbers. Can you consider that? Just let that sink in for a second. It's pretty cool. So, the imaginary letter I. Let's look at a basic one. We can take the square root of a positive number like the square root of 9. That equals 3, because 3 squared equals 9. Technically, the correct answer is plus and minus 3. Remember, if you take the square root, and we'll talk about why, you have the positive version and the negative version of that number. Because let's look at it. If I take the positive version of 3, 3 squared technically means 3 times 3. That does indeed equal 9. Gets me back to my original. But also the negative version of the same number, negative 3 squared, can be written as negative 3 times negative 3. That also equals positive 9, because when I multiply two negatives together, it gives me a positive number again. That's why the positive version and the negative version of the number, when you take the square root, exists. So please, please, please remember, when you take the square root, you always have the positive and negative version of that number. If you answer something on the test and you don't put plus or minus by it when you're taking the square root, it will be wrong, unfortunately. So please remember that. So that works with the positive. But when we try to take the square root of a negative number, like the square root of negative 9, let's say, we can't do it because there's no number that exists that when multiplied by itself will give you back that negative. Like I did in this situation, it either has to be 3 times 3 equals 9 or negative 3 times negative 3 also equals 9. That's why the imaginary number system had to be created by mathematicians long, long time ago. So these two rules are very important. The imaginary unit I equals the square root of negative 1, and the inverse of that, I squared, equals negative 1. So again, to get rid of this, you have to square both sides. That's how they get it. I squared equals negative 1. So remember both of those things, please, to consider, because you will encounter situations when you're working with complex numbers where you do I times I, and you have to know that anytime you do that, that equals negative 1. So let's put this into practice a little bit, and I want to show you why they had to invent the imaginary numbers. Because if I take the square root, let's look at the first example, square root of negative 121. Well, I know the positive version, the square root of 121, is plus or minus 11 because it's a perfect square. So I can assume then that this will be plus or minus 11, but I need to show that I've entered into the realm of imaginary numbers because, again, there's no number that multiplied when itself will give me back a negative number. And I show that by using the imaginary unit I, imaginary letter I. So to finalize this answer, I have 11I. Now I want to prove to you why this exists the way that it does. If I do the positive version of 11I squared, this power, what this really means is that it's 11I times 11I. Now 11 times 11 is 121. And I times I, remember, I times I, let me rewrite this up here a little bit. I times I equals I squared, and that equals negative 1. So I times I is I squared. I'll write that, but then you must know that 121 times I squared is negative 1. And then finally, negative 1 times 121 is indeed negative 121. So this is why the imaginary unit I had to be created, because then when you multiply 11i with each other, it will give you that negative number back in what you started with. So this is why the I has to be there, plus or minus 11i. If you tried it with the negative version of 11 down here, you would get the same answer of negative 121. Now let's move on to the next example. Square root of negative 28. Now again, the first thing you would do when taking square roots is check to see is the positive version, if it's negative, square. So again, if the positive version is a perfect square, then you can break it down just like I did in the first example. But the square root of 28 is not a perfect square. So that means I have to do my factor tree and simplify the radical. I can use this one, the negative 28, doesn't matter. You need to remember is that if you take the square root of a negative number, you need to have an I in your answers. Remember, your final answer has to include an I so that you can tell me that you've entered into the realm of imaginary numbers. Now, let's break down 28. The only factors of it are 7 and 4. 7 is a prime number, so it doesn't break down anymore. But 4 can be broken down to 2 and 2. So I'm looking for pairs. I have a pair of 2's. And so in this case, when I break this down, if we consider this radical to be a house, you need to have a partner to come out of the house. Or if it's a jail cell, you need to have a buddy to help you sneak you out of jail. Whatever you can think of to help. In this case, the 2's are buddies. They have a buddy. The 2 has a buddy. It's another 2. So they can come out of the radical. And again, out of the radical. They come out as just 1, 2. So the two 2's come out as 1, 2. Then I have to write, and again, in order to free up the negative over here, that negative that exists underneath the radical, just like over here, it came out as an I. Now I have to include the radical still to simplify it, and I have to write what's left underneath the radical. In this case, the only number that exists, because this 4 broke down to these 2's, the only number that exists is the 7. And I need my plus and minus to indicate that the positive and negative version work. So this is my final answer. This over here was a perfect square, so I can jump right to my answer. This one was not a perfect square, so I had to break it down and simplify the radical. Remember, I needed the I outside of the radical because of the initial negative that existed inside the radical. I have to free that negative by putting an I and telling everyone that I have entered into the realm of imaginary numbers. Alright, moving on. Multiplying. When multiplying, you treat it just like a variable at first, if there's an I. This 5 and this 2 are coefficients. They multiply on each other. It's as simple as 5 times 2 is 10, and there is nothing to interact with the I, so it just becomes 10i. And then one more. Same thing over here. This is where when i's are multiplied on each other, you have to remember this rule right here. So negative 3 times 2 becomes a negative 6, but then I times I becomes an I squared. And you remember that I squared equals negative 1. So then I get negative 6 equals negative 1. And finally, negative 6 times a negative 1 gives me a positive 6. And I'm done.